Do you have the copy of these handouts? I gave it to you a few weeks ago, probably 2 weeks ago. Still have one. I have 5 copies over here. If you don't bring them over, I can give 1 copy to you. So these are printed out from the textbook to evaluate the performance of the ADCs. Do you have them? I gave it to you 2 weeks ago. So today's goal is to look at the quantization errors of the ADC and also the nonlinearities, including differential nonlinearity and integral nonlinearity. You can see the description from the handouts, and these are directly printed from the textbook. So how do you calculate it and how these were getting simulated? If you click the link over here for the course project, so the entire diagram starting from sample and hold and comparator, and then the SAR block. The DAC, so the DAC converts all the digital values into analog voltage and feed it back to the comparator to get you all the comp outputs, right? For the SAR ADC, for the SAR block. And this is a row of D flip-flops, and you have a clock at rising edge to kick out the final values. And this is R2R DAC again. Okay, keep in mind the standard ADC doesn't have the second DAC. So the reason we are getting a second DAC is try to plot the final output. If you don't have this final DAC, and you are getting 8-bit or 8 bits of digital output, eventually have to plot like 8 signal lines. Sometimes could be difficult to look at. So in order to evaluate the results, we use the final DAC, just trying to run the final results. Okay, look at the final results. So sample and hold circuit, we went through the circuit design last time and also probably on Friday last week. And we have gone through this for twice almost. And there will be quizzes on this. Also the timing diagram, there will be a quiz on that, for the timing for the SAR ADC on Friday. So you need to know every single detail about this one. If you don't, please watch the video again. Important circuit. So that's a simulation for the sample and hold. I put everything to a block and I simulate it. Sample, track, and hold. So the digital conversion happens during the hold period. That's a comparator. It's an op-amp design because this is not an analog class. We're not going to get into the details about the op-amp design, but this is one op-amp that I directly used from the textbook. So it's mainly for analog applications, but for this one, it has a weakness because it's not really good at amplifying lower voltages. So if you look at or another term, it's not a reel-to-reel oscillation. So if you look at this one, this curve, I ran it for about like 40 minutes a few days ago. You can see I showed you this final output yesterday. Remember this one? So that's the ADC's output. I got a black line. Here is a sine wave. And the blue line is a digitized signal, but through the final DAC. So eventually, because the ADC's output should be 8 bits of digital signals, right? You couldn't see it clearly compared to the analog signal. So you have to run it through the DAC. So eventually, the second DAC output from the second DAC looks like this. You can see all these little stairs. And the thing is, I want to see the standard ADC curve to evaluate the quality of it. So if you look at the handout here, usually what we do is whenever you get an ADC, you plot this curve first. Do we have that? No, it's just that, not ADC, but similar. So if you look at this is the DACs. So the input is the digital signal and output is the analog signal. So for ADC, just another curve from the textbook is looking at it. So the x-axis becomes the analog signal input, and the y becomes digital signal output. That's for the ADC. But now as for DAC, you can see whenever it reaches the next step, it should jump to another value. And we're going to get into the details today, every single detail about how to calculate it. But you can see that the straight line here is the ideal value with all the ideal values. And all the stairs are the ADC or DAC's output. They are stairs. In that case, there will be errors because it's not perfect resolution. So eventually there will be errors. But there will be more problem for this design. So I'm trying to change the comparator to a different one that I found online. I want to compare the performance of these two different competitors. I can see there's one example from here. I think that's a let me just search it. I think this one, 600 level VLSI design class in Columbia University. It's a 2-semester, 6 credits class. So students design ADC in the first semester, PhD students, okay, not undergraduates. So you guys are doing pretty much the same thing. This is so hard. It's because it's an undergraduate and graduate level. It's a 400 level class. That's why. So anyway, so Columbia University has all these PhD graduate students design the ADC in the first semester, and the second semester they send it to, I think that was IBM, 130 nanometer technology, and fabricated. So the second semester they got a chip bonded to the package and put it on the, I believe, a PCB board. Yeah, let me see if I have a demonstration somewhere. Simulation results. Okay, simulation results. Things like this. Okay, there will be little stairs. The straight lines are perfect, and the stairs are the ADC output, but being converted to analog signal from the DAC. Because ADC's output are 8 bits. And there will be other parameters to analyze, but including INLs and DNLs. These are the timing sequence. So we look at the sample and holding circuit. We use the same sample and hold circuit, but the comparator is different. So they use the comparator that has appeared in a lot of other literature papers, published papers as well. So I'm thinking probably it's going to be a real-to-real oscillation. So eventually we'll probably change or replace this comparator with the one they used. But let's take a look at the demonstration, if there's a demonstration somewhere. I think.
Hi, I'm Dhruv.
I'm Shikhar.
I'm good.
Done by 3
We are
graduate
electrical
students.
engineering students at Columbia University.
Show you that piece.
Today we are going.
Okay, here. You can expect what can be done in the future. Okay, so the ADC doesn't have a DAC, right? So eventually the ADC doesn't have the second DAC. ADC is just ADC, so it's A to D, right? And it's a parallel output, parallel digital outputs. Eventually the outputs are 8-bit digital outputs. So what they did is, you can see all these resistor strings. Is that familiar to you guys? What is that? It's R2R DAC. Okay, so the ADC they designed has an 8-bit digital output, and eventually these 8 bits are connected to, like for example, these lines, right? So these are connected to all these R2R DAC, and eventually it's being converted to an analog signal analog signal to the output on the PCB. So they got a chip, got a R2R string, and analog output here. So what's happening is they use a music signal from the laptop or your phone, doesn't matter. So have a jack header connect to it and split the two wires, because these two wires is one is analog signal, one is ground, and they split them and plug. Oh, they didn't, because they use a jack header here as well. It's an audio jack. So eventually plug it in and split the signal on the PCB. So that's the analog output, keep in mind. So from the speaker here, it's an analog output. It's analog voltage. So that analog voltage of the music is being digitized by the ADC they designed, which is the ADC we display on our website. The same, almost the same structure. Okay, and that music is getting digitized. Eventually, you are getting all the stars, and these stars, digital signal like 8-bit parallel. Okay, and this 8-bit parallel signal is converted to analog stars by this R2R string. Okay, so eventually the output will be stars but analog voltage. That makes sense? So the analog voltage carries information, which is the music. So they can play the music on the PCB. It's a really fun project. So seems like unnecessary because the output from this cable is already analog music. You can just amplify it with audio amplifier and play it, but it's different, right? Since you digitize it, so that means the way you digitize it has to be accurate. Every single analog point in the analog signal of the music has to be digitized and being registered as a digital level. And then that digital signal is being converted back into analog and you play it back. And you listen to that, it's still the same song. If there's any distortion or anything getting missed, losing any information from the digitization, you are not going to hear or recover the same song, right? So eventually, I think this was pretty successful.
This is the audio.
Oh, sorry.
When the music is played directly onto the speaker.
So it was able to play that song. Okay, it's not changing anything. But through a redundant digitization. Okay. But that works. So my goal is, if this ADC works, eventually we are going to integrate it into our SoC design, the microcontroller EN design from the 6502 from WDC. That little microcontroller already got taped out, so we are going to integrate this ADC to that to make it full-fledged microcontroller in the future. So that microcontroller will have a CPU, have all the memories, and also ADC on it. If this works, this will be our own ADC. Yeah, a good reference. I think I got a link here, but it didn't work really well. But I can directly search this design. Should be able to see it. So now you got an idea about the op-amp, the comparator one to replace. So which is this comparator will be replaced by the one. Let me show the structure of it. So the one thing they didn't do well is schematic. They are really low resolution. Couldn't even see the details about the sizing of the transistors. Anyway, so this is a clocked differential comparator. It's claimed to be real-to-real oscillation swing, so which means low signal can swing down to 0 and high signal can swing up to VDD. So in that case, whenever the input is low, it will be able to get digitized instead of getting lost. You can see when our input signal is low. Let me see if that makes sense to you guys. This simulation result is from our ADC, right? This is the final ADC design. And one quick question, just let you guys think about it, right? For the ADC design, if I want to simulate and eventually see a result like this, what type of analysis I should run? So what's really going on is, if you look at the final output, like this. All right. So it's a sine wave in time, and I'm able to see the little stars over here. It'll be very similar to the standard curve of the ADC like this, right? So you want to run a straight line, which is the voltage sweep, and eventually see the outputs. And the outputs has to be the final second DAC's output, because the ADC's output is 8 bits. But eventually this is just a one node, right? You can see it's just being probed. It's just one node. So the thing is, can you just simply use the DC sweep to get this curve? So what does DC sweep mean? In SPICE, this can be interview questions, super basic. Okay, DC sweep, transient analysis. Still remember these terms? AC analysis. Okay? Maybe they'll ask you, what is the DC sweep in SPICE? Can you write a SPICE code in DC sweep to run this kind of simulation during the interview, right? Can you run the transient analysis? So transient analysis is just in time domain. You do a dot trend from 0 to 1 second and 0.001 second to plot a point for the simulation as a resolution, right? So DC sweep is dot DC, and you are sweeping, for example, V1 source from 0 to 5 volts and 0.001 volt to plot a point. So it's running a DC sweep from 0 to 5, and every 0.001 volts you plot a point, and then you look at the output. You probe whatever you want to probe, okay? So the input is going to be linear because you are sweeping your input linearly. It's 0 to 5, and the increment is 0.001 volts. So in that case, can I use a DC sweep to analyze the performance of the ADC? Because ADC is taking analog voltage, right? Analog voltage input, and convert it to a digital output. So I want to know every single analog voltage input of the ADC and look at the output and see if it's accurate enough. All right? Can I do a DC sweep? Why not? Is there any time domain in DC sweep? There's no time. However, your ADC is being clocked. Is that correct? Is your ADC get clocked? You don't know? Is the ADC getting clocked? Yes, you got a clock. And you're waiting for the 8th, 9th clock to get the final output. So you need to run the ADC in the time domain. So time is a really interesting parameter. Okay? DC sweep doesn't have a time. DC sweep just one time point. There's no extension on time. So ADC needs to run in time because it's been clocked. Okay? It has to be clocked. You have to run different states in order to get the final output. So DC sweep sounds like it's going to work because I'm providing different DC voltages to the input and I'm trying to get an output. Actually, it won't work. It will work in real world when you are having different analog voltages being put into the ADC at different time points. Then you need time. But if I just do DC sweep, there's no time. So that wouldn't work. Eventually, if you do a DC sweep to the ADC, you are getting a straight line. It's only taking the first point and giving you an output. It's not doing anything else. Because clock won't start. There's no time. So DC sweep doesn't work. What can I do? Which one should you use? Whatever involves time, right? So transient analysis has time in there. So x-axis has to be time. However, when you are looking at the handout here, I gave this handout to you guys a few weeks ago. If you don't have it, I don't have like a few copies. There's one more copy over there. But if you don't have one, you should probably in your backpack or somewhere. So, but when you are looking at the voltage input and output of the curve, no matter it's a DNL or DACs or ADCs, so both x and y axis are voltages. Both are voltages. So seems like it should be a DC switch. But we cannot do DC switch because there's no time. What's the conclusion here? Conclusion, you still cannot do DC switch. And have to run transient analysis. And have to use give different voltages at different time points. That's it. Okay, run transient analysis like this. So how can I form a straight line like this linearly? So remember the pulses. The pulse signal has starting voltage, that's the end voltage, delay, rising time, falling time, T on, and period. These are all the parameters of the pulse function. So in order to form a linear line like this, what you can do is set up a pulse function, but never run a pulse. So do a pulse function starting from 0 volts to 1 volt, because this is the 1 volt 1 volt VDD. Okay, just keep in mind it's not 5 volts, but you guys are going to use 3.3 volts, I think. But anyway, just logic 0 to logic 1, and time delay doesn't matter, just 0. Okay, and make the rising time really long. So let's say, so what did I use? What did I use over here? See, I used 2 milliseconds. Just 2M. Falling time, 2 milliseconds. We're not even looking at the falling time, this is okay. T on. Doesn't matter. T on, let's say 1 millisecond. Period. You have a rising edge, falling edge, and T on. So in total, it's already 5 milliseconds. Let's make it like 6 milliseconds. So it's going to form a square wave or triangle wave. It's a pulse, but because we make the rising edge so long, so it looks like this. Okay, a pulse. Looks weird. And then we only simulate it for 2 milliseconds. 2 milliseconds. So we are basically forming an input ramp. It's a linear ramp. Okay, for the simulation. So in that case, you are able to input a linear voltage sweep in time. And because it's in time domain, right? So time domain is 2 milliseconds. So, and every single, I don't know the resolution for the points, but it's probably by default, it's giving little voltage points input every single something like microseconds. So these will be provided to the ADC's input, and the ADC, because you have timing here, and eventually the clock will work. So it's going to digitize the signal and eventually give you this type of output. And it looks like this, the final output, and it doesn't really work well for the low voltages, which is fine because usually it's definitely not ideal. You know, but if you look at the one I simulated, I avoided that low voltage. See this one. It's 100 millisecond. It's 100 millivolts swing, peak to peak. No, it's 100 millivolts, 100 millivolts amplitude. So totally 200 millivolts peak to peak. And the DC offset is 500 millivolts. Let me draw it for you on the paper. I think I was wrong. Let's see. This is about 600 millivolts, and this is about 200 millivolts. Yes, that's right. So totally, I have 1 volt for the range, and this is 500 millivolts. So my sound wave or analog signal input looks like this. So there's no low voltage. So this range is bad because the ADC cannot do it really well over here. So I just avoid it, right? But there might be some situations that you have to get a wide swing range. So the analog signal probably is gonna swing like this, right? And then you have to, maybe there will be a chance this one enters that zone here, and eventually you're getting a lot of errors. However, if you replace that comparator with the reel-to-reel swing, you may get a better performance. So this is part of the project. I'm gonna work on it as well and see if I can make it. Otherwise, I'll let you guys try it, explore this a little bit. But this op-amp provided by the textbook already works. It's just not perfect because the low voltage range is having a lot of errors. It's not reel-to-reel swing. Another thought here is why the signal is always sitting in the middle. So that's a very good thing to think about. This signal is already pre-amplified and processed. It's not directly from the sensor. You will never use analog signal directly from the sensor because it's not being processed. You can see this is already pre-processed. That is why it's adding a perfect DC offset. It's lifting the AC swing to the middle of the range. So have the best swing room to the top and bottom. Imagine if you lift the analog signal, for example, to here, right? And if your signal is gonna swing like this, you'll get cut off at the bottom. So the best way is to lift it to the middle. Keep in mind, it's very important. Lift it to the middle so your signal can get a wide swing to both sides. All right. So that being said, your analog input from the sensor can be anything. It's unpredictable. For example, the sensor is giving you something like this, and here this is your 1 volt range over here on the top, and the sensor is outputting something like this. It's very likely. And there's the little DC offset, which is, for example, 0.1 volt. So what's the first step? So that's the original analog signal from the sensor. Keep in mind, very practical. Already happened to a couple of senior SEM projects, and a lot of people don't know how to do it. So this one, first of all, you need this. High pass filter, okay? To remove the DC offset. And for here, you do a superposition. If it's a 1 volt range, you add a 0.5 volts over here. It's a DC voltage. So it's gonna lift that AC signal. The AC signal is getting blocked. No, the DC offset of the AC signal is getting blocked by the capacitor, but AC is able to pass. But DC is getting blocked. So you are getting 0 DC offset over here, and then you add a superimpose 0.5 DC voltage to it. It's going to lift the signal to 0.5 volts. So eventually your output over here ideally should be 0.5 volts and have this AC signal over here. Make sense? That's the first step. Always high pass filter. If you need to do some low pass filtration to get rid of the high frequency stuff, then just do it. Otherwise, you don't have to. But usually you do. Okay, there'll be a lot of high frequency noises, and also the 60 hertz from the outlet as well. But anyway, let's just do this first, and eventually you got this one, and then you amplify it, right? Amplify it. It could be a this is a non-inverting amplifier. It's RF, R1, VL. But you can add more stages depending on the need for the gain. Okay, but this is just a basic needs over here. So this one remove the random DC offset here first, and then amplify it, and then lift it, and then amplify it. So after the amplification, you are getting this 0 to 1 volt range. The voltage becomes bigger, but still swinging around that DC ideal DC offset in the middle. So it's gonna do this, right? Do this. So you may need more stages than one. So in that case, eventually you have this AC signal swing around that ideal or better DC offset, which is in the middle. It's gonna swing like this, and eventually you can digitize it. Okay, that's the standard steps of processing analog signal from the sensor with ADC. Okay, so if you do the ADC, you got a digital signal, you can store in the memory, you do whatever computation with the CPUs, whatever. Because that's all the following computation. But this is the pre-amplification stage for these ones. Pre-amplification. So you can see the goal is to swing your analog signal around that 50% of the range, like this. Okay. Now let's see how do we analyze all the DNL and INLs. Let's start with the DAC first. So that's the example from the handout given to you. For example, there's a DAC. It's giving you these parameters. There's a digital input, and there's a voltage output. This is a DAC, right? Voltage output. And there will be an ideal output, ideal voltage output. And the values are, because the digital input is a 3-bit DAC, so 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 0, 1, 1, 1, 0, 0, 0, 1, 1, 1, 0, 1, 1, 1. So these digital inputs, total 8 of them. So the actual voltage outputs are 0 volts, 0.625 volts, 1.5625 volts, 2 volts, 2.5 volts, 3.125 volts, 3.4375 volts, 4.375 volts. And ideal outputs are 0 volts, 0.625 volts, 1.25. It's adding 0.625 each time. 1.875, 2.5, 3.125, 3.75, 4.375. Okay, and when you plot it, zero, 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 001, 010, 011, 100, 101, 110, 111. These are the digital inputs. So ideally, it should be a linear curve like this for the output. Everything should fall on the ideal curve like this. That won't be the case, but ideally it should be like this. So the first one definitely 0 is to 0 volts, no problem. The first one should be 0.625 volts for the transition, right? So it's a DAC, so the digital input, whenever the digital input jumps to 001, it should give you exactly 0.625 volts, ideally. And for the second one, it should be 1.25 volts, 1.875 volts, 2.5 volts, 3.125 volts, 3.75 volts, 4.375 volts. So ideally, it looks like this. However, you know, one step, second step, third, fourth, fifth, sixth, seventh. Yeah. ADC has a finite resolution, so eventually you'll see stars. However, there will be nonlinearities, which are these values. So instead of having, so the first one is okay. So you can see 0.625, 0.625, it is fine. Okay. However, when it should reach 1.25 volts, which is here, it goes up to 1.5625 volts instead. But it's still lower than 1.875, so it's going to be in the middle. Reaches here, 1.5625 volts. And then it introduces nonlinearity to the results. And so this involves two different terms and being calculated in two different ways. The first one is called DNL, and the second one is called, it's not one, it's page 3. And the second one is called INL. Now let's see how they were calculated. Just for this point, for DNL, you look at the digital input, now this is number 2, right? So it's called, labeled as DNL 2. So DNL is, you are using the actual step size minus the ideal step size, which is 1 LSB. So the 1 LSB in this 3-bit ADC is going to be 0.625 volts, because this is 1 divided by 2 to the third. 1 divided by 8. No, 5 divided by 8. Which is 0.625 volts, which is 1 LSB. So every digital LSB increment should give you a 0.625 volts increment.
Is the DNL like a error measurement? Or?
Yeah, differential. Differential and integral. But they are measured like this. It's not really integrating, but it's measured like this. So for DNL, it's measured as the actual step size minus the ideal step size. You can see the actual step size is 1.5625, right? So it's from this point to this point. So this point's voltage is 0.625 volts. That's the actual step size, right? And this one is how many LSBs? It divided by 1 LSB. You are getting how many LSBs? And this, how many LSBs minus 1 LSB will be the final DNL. So the unit will be in LSB. because the step size over here should be 1 LSB. That's the ideal step size, which makes sense, right? Every single digital input is giving you 1 LSB increment for the analog output as well, which is 0.625 volts. So eventually you get actual step size in LSB because you are dividing the LSB's voltage value. So you're getting how many LSBs for that actual step size, and minus the 1 LSB, you are getting the difference between actual and ideal in terms of the LSBs. Does that make sense? It's basically the actual step size minus the the ideal step size. That's it. But the unit you convert it into LSBs. Question on this. So the answer of this one is about 0.5 LSB. So do the calculation. All right, and now let's look at the next one, which is 2 volts. So supposed to go to 1. Here is 1.25, but it goes to 1.5625, and here should be supposed to be 1.875, but it goes to 2 volts. So, which is this guy goes to 2 volts. It's below 2.5, so it should be labeled here, 2 volts. So which means this one got extended to here, and directly jumps whenever it reaches this digit. It jumps to 2 volts instead of 1.875. So how to calculate the DNL here? If you look at the label, it should be labeled as DNL 3. Okay, it jumps at DNL 3 at the digital 3 input. So because the definition is the actual step size minus the ideal step size, and the ideal step size is always 1 LSB, it's not changing. But actual step size, you just look at the curve. It's basically the last voltage level, where that is at, and you have the final voltage output over here minus the previous voltage, which is getting the actual step size. So in this time, you are using 2 volts over here minus 1.5625 volts, and divided by still the same 1 LSB's analog voltage, which is 0.625 volts. And this is how many LSBs you have for that step, and minus 1 LSB, still 1 LSB always. And this is going to give you the second or DNL 3, which is negative 0.3 LSB. Calculation. And now you can see the next point, it comes back to 2.5 magically. It just happens. It's okay. Right? Let's just analyze what the DNLs is. So this one has 2.5 at the next point, which is exactly here on the curve. So in here, it's going to jump to this point and then do this. So the curve looks weird. If you block the black one, just look at the one over here and following the red one, it looks weird. Like then a very small step. It's like our circuit. So this one is DNL what? DNL 4, right? Because you are looking at digit 4. DNL 4 is what? Which minus which? Just tell me. Which minus which? What's the step size from here to here? What's the step size? This one minus this, right? Here is 2.5. The previous voltage is 2, so it's going to be 2.5 minus 2 divided by 0.625 minus 1 LSB. And that gives you negative 0.5 LSB. Okay? And the next one, is 3.125 becomes normal. Becomes normal. So there's no DNL here for this point. 0.125 is the same. Keep in mind this is the ideal ones. This ideal ones has a 0.625 increment every time. Okay, the next one. 110 for 110 over here. So when it reaches 110, it didn't jump to 0.75 volts. Wait, did I draw it incorrectly? 110. I probably didn't label it correctly somewhere. 0.625, 1.25, 1.2.5. This one 3. Looks right. Did I skip one number? No, I didn't. 110 here. Oh, like this, right? 0.125 is still accurate, but for 0.75 is not accurate because it goes to 0.4375 instead of 0.75. So what is the DNL now? What's that?
I've got like a question. So you were talking that there was that dead band for the lower voltages.
Yeah.
But it looks like the lower DNLs are actually better than the higher, except like the 7th one.
Mhm.
So I was just wondering, like, how can we tell the dead band from this?
Yeah, this was made up.
Oh,
Just example from the textbook. You can do whatever you want. Okay, a good question on that. So for this one, we have 2 more points, right? So we don't have time to run the quiz again. So Friday maybe let's do 2. I'll let you know what our quizzes are. Okay. It's the same thing, right? You do it today or do it on Friday. Friday is actually better. Have more time to prepare for that. Okay, let's look at this one. This is DNL what? We don't want to finish the example, so this is DNL what? DNL 6. Which minus which? What's the actual step size? Which minus which? Step size 3.4375 minus what? 3.125 divided by 0.625 and minus 1 LSB. And you are getting negative 0.05 LSB. And the last one looks like the actual output is fine. However, we are looking at the difference, right? Even though it comes back to the ideal point. But the thing is, the transition has a very weird step size. So which means the DAC has a nonlinearity. Even though the final output is fine, but the step size is weird because the previous one was off. So for the final one, it reaches this point, which is okay for the absolute value, but it has a DNL here. DNL 7 will be, this is the actual step size, right? It's going to be 4.375 minus 3.4375. This minus this one, remember? This minus this one, the step size. Divided by 0.625 and minus 1 LSB. And this is giving you 0.5 LSB. And the question on this, DNL analysis for DAC. Any question on this? So on Friday we'll finish these examples, including INL of the DAC and also DNL and NL for the ADCs. So think about this. Whenever you are reporting an ADC design, this will be a really exciting project. Just think about it in the future. So we can get a ADC tape it out and probably put on the journal article. So when you are doing analysis in your course project, I'm asking you, what are the DNL and NLs of your ADC? So you are going to run a simulation like this, and you can see this curve, and I zoomed in, and I zoomed in further. It looks like this. You just have to figure out a way to make it fire, right? Which point you are looking at. So these are I was measuring the ADC's step size. It's about 0.6 millivolts, and ideally it should be 0.4 millivolts. If it's a 1 volt range for 8 bits, you use 1 volt divided by 1 volt divided by 2 to the 8th, because it's the 8-bit ADC. And this is 1 volt divided by 256 steps. So the resolution should be somewhere around like 0.39 millivolts. Wait, volts or millivolts? Millivolts. No. Yeah, millivolts. So I was getting like 0.5 to 0.7 millivolts. Right? So that's something you want to look at, and also you plot this curve, and eventually you have to look at the points, find out the maybe plot the entire DNL and INL for each point and make an average. Or you can plot a diagram to have all the DNL and INLs being plotted, and eventually just display the whole the entire output, the entire result, instead of average value. So eventually the DNL and INLs will be a range. So for example, you will see parameters like 0.5, 0.1 LSB to 0.5 LSB. So that's a range for the DNL for the whole for the entire all the transitions of all the points. So the maximum DNL or INL you are getting is 0.5 LSB. The minimum was 0.1 LSB, depending on which point it's being converted to its corresponding digital value. So this is the parameter you are looking at eventually, right, to evaluate the performance of the ADC or DAC. So we'll look into these two parameters, nonlinearities of the ADC on Friday, right? And the quizzes are, first one is a charge pump. I'll just show you to be fair. So study this, okay? That's the goal, okay? So I don't mind to tell you what will be on the quiz. So the first quiz is quiz 12, is the charge pumps. And charge pumps, I showed you a few different circuits of the charge pumps, including the Dixon's charge pumps, and also this charge pump. And this charge pump has several key points you need to know, including the sizing of the transistors. And this doesn't have to be big. This is big because it's driving this point for the following circuits. And this capacitor doesn't have to be big because it's not driving, it's only driving the gate. The gate doesn't have a static current running through it because it's a CMOS transistor. And this capacitor has to be big because you need a big reservoir to drive the following circuit. And this PMOS is handling a voltage larger than VDD, so this PMOS needs to be in its own well, right? So when you are doing a well layout in electrical VLSI, how do you implement it? When you are laying out all these PMOS and NMOS transistors, how do you separate the unwell of this guy from other unwells? So you need to display, you need to draw it on the paper. You know what I mean? The high voltage PMOS needs to be in its own well. I explained this for at least twice in the previous lectures. So that's the first one. The second one will be the timing here. So I missed a couple of you guys on the lecture on Monday. And so definitely go through this lecture and learn all these key points and why we design the time like this. And that's a key point to make the ADC functioning. That's the whole design of my course project I designed since like 2-3 years ago.